Hello everyone, welcome to this KTHM e-learning channel. I am SK Marathe. Now this is second lecture of T.Y.B.Sc Physics paper first, Mathematical Methods in Physics. In this lecture, we are going to discuss spherical polar coordinate system and transformation equation between Cartesian and spherical polar coordinate system. Let us start. In previous lecture, we have studied Cartesian coordinate system. As we have seen, it uses three coordinate axes which are mutually perpendicular to each other and three coordinates x, y and z to specify position of point in three-dimensional space. This system is applicable to problems which have rectangular symmetry. But there are many physical systems. There are many physical systems which have spherical symmetry. For example, electric potential of sphere, gravitational potential around Earth, and so on. To treat this system, to describe this system, the coordinate system used is spherical polar coordinate system. Then, what is spherical polar coordinate system? Let us see. In spherical polar coordinate system, the three coordinates r, theta, and phi are used to specify position of point in space. Then let us see what is r, what is theta, and what is phi. This r is the distance of point P from origin. It is the distance of point P from origin. That is, this OP is the r coordinate. Value of r varies from 0 to infinity. Is when point P is at origin, the value of r is 0, and as the point goes away from origin in any direction in three-dimensional space, as point P goes away from origin, value of r increases. Then the second coordinate theta. This angle made by this line OP, with z axis is theta coordinate. It is also called polar angle. This angle theta is ZOP. This angle ZOP is theta coordinate. It is also called polar angle. The value of theta varies from 0 to 180. 0 to 180 is when point P is on z axis, value of theta is 0. As the point goes away from z axis, then value of theta increases. And when the point is on negative z axis, the value of theta is 180 degree. This way, value of theta varies from 0 to 180 degree. Then let us see third coordinate phi. If you draw a perpendicular from point P on xy plane, draw a foot perpendicular from point P on xy plane, let it intersect at point Q, then connect this point Q with origin, then angle made by OQ, which is projection of OP on xy plane. This OQ is nothing but projection of OP on xy plane, and the angle made by OQ with x-axis is phi coordinate. That is, this angle XOQ. XOQ is phi coordinate, and value of phi varies from 0 to 2 pi. It is on the x-axis. This angle is on in this xy plane. When the point is in first quadrant, this xy first quadrant, then value of phi varies from 0 to 90. When in second quadrant, that y2 minus x, value of phi varies from 90 to 180 degree, and from minus x to minus y. In third quadrant, it varies from 180 to 270, and in fourth quadrant, from minus y to x, in fourth quadrant, it is 270 to 360 degree. In this way, this value of phi varies from 0 to 360 degree, 0 to 2 pi. In this way, these three coordinates used in spherical polar coordinate system are theta, phi. What is r? R is the distance of point P from origin. What is theta? It is angle made by line OP with z axis. And what is phi? It is angle made by OQ with x axis, where OQ is projection of OP on xy plane. Then next topic, coordinate surfaces. That is, we have to see coordinate surfaces in spherical polar coordinate system. In three-dimensional space, as we have seen in Cartesian coordinate system, this definition we have already seen in Cartesian coordinate system, that in three-dimensional space, if one coordinate is held constant, out of three coordinates, if one coordinate is held constant and other two coordinates are allowed to vary, the resulting surface is called coordinate surface. Let us see one by one. R constant surface, that is r coordinate. If r coordinate is held constant and theta and phi allowed to vary, that is this distance OP, if this is kept constant, then if we connect all points in 3D space, if we connect all points which are at a distance r, if we connect all points which are at a distance r from origin, then we get a surface of sphere. Surface of sphere. Therefore, this r constant is a surface of sphere. Example of this football. Then all points on the surface of this football, all points on the surface of this football are at same distance from origin, and that distance is nothing but radius of football. Therefore, this is spherical surface. The same way, spherical, if this r is held constant, and if we connect all points which are at a distance r from origin, then we get a spherical surface. That is, all points on this surface have same value of r coordinate, but value of theta and phi coordinate vary from point to point. Then what is unit vector? This unit vector, ER unit vector. This ER unit vector is a normal to the surface at a point. This ER unit vector is normal to this spherical surface at point P. Now, what is direction of this ER? The direction of ER is in the increasing direction of the R. At point P, this is the increasing direction of R. Therefore, this is the direction of the unit vector ER. Then second surface, theta constant surface. Theta constant surface. This theta constant surface is a surface of a circular cone, with z axis as its axis and origin at the vertex, as shown in origin at the vertex. As shown in figure, this is the conical surface with its vertex at origin, and axis of this cone is along z-axis. Axis of this cone is along z-axis. That is, if we connect all points which make angle theta, all points when connected to origin, that line makes angle theta with z-axis. If we connect all these points, then we get a conical surface. Therefore, this conical surface is theta constant surface. Let us see from this figure. In this figure, if we see any point, if we observe any point on this conical surface, and if we connect that point with origin, then that line makes angle theta with z-axis. That is, for all points on this conical surface, theta is constant. Distance of point from origin varies from point to point. Therefore, r varies. And foot perpendicular on xy plane also varies from point to point. Therefore, phi also varies. But the theta is constant for all points in this conical surface. Therefore, this is theta constant surface. All points on this surface have same value of theta coordinate, but value of r and phi coordinate vary from point to point. This theta constant surface. Then unit vector E theta. This unit vector. This unit vector is normal to the surface at a point P. This conical surface, and at a point P, this is normal. This arrow shows the normal. And the direction of this unit vector is along the increasing direction of theta. This is the increasing direction of theta. Here, this is the increasing of direction of theta. Therefore, this is the direction of unit vector at point P. This direction varies from point to point. Then third surface, phi constant surface. If phi is held constant, phi coordinate is held constant, and r and theta allowed to vary, then we get this half plane. This half plane with one edge along z-axis. This plane with one edge along z-axis. Then this is phi constant surface. If you observe all points on this, if you draw a foot perpendicular from any point on this surface, if you draw foot perpendicular from any point on this surface, then it intersect on line OQ. If you consider this point, then the foot perpendicular is on line OQ. For this point also, the foot perpendicular is on line OQ. For this point also, the foot perpendicular is on OQ. That is, for all points on this surface, value of phi is constant, but value of r, that is distance from origin, for this point, for this point, the distance from origin varies, that is r varies, and angle made by line connecting with origin also varies, that theta varies, that r varies on this surface, theta varies on this surface, but phi remains constant. Therefore, this is phi constant surface. All points on this surface have same value of phi coordinate, but value of r and theta coordinate vary from point to point. Then unit vector E phi. This unit vector, again this unit vector E phi is normal to the surface, to this phi constant surface. Normal to the phi constant surface is E phi. And direction of this E phi is along the increasing direction of the phi. This is the increasing, at this point, this is the increasing direction of phi. As phi increases, the direction varies. But at this point, this is the increasing direction of phi. Next topic, coordinate curves. That is coordinate curves in spherical polar coordinate system. Three curves we have to see. The first one is R curve. Is R curve. The definition of this coordinate curve is, if two surfaces intersect, then the intersection of two surfaces gives a curve. This R curve is intersection of theta constant and phi constant surface. Theta constant is a conical surface and phi constant is a half plane. Theta constant is a conical surface, phi constant is a half plane. Then intersection of this conical surface and the half plane is this line OP. This intersection is along line OP. Therefore, this line OP is R curve. This line OP is R curve. Along this line, only R coordinate varies. Along this line, only R coordinate varies, while theta remains constant and phi remains constant. Let us see in detail in this figure. This is line OP. If the point is here, then this angle made by OP is theta. Projection is on this line. The angle is phi. If the point is here, R is increased, but angle made by OP is again theta. Projection is on the same line, therefore phi is same. If the point is moved here, then again angle made by line OP remains theta, put perpendicular on the same line, therefore phi is constant. And if the point P is here, then also theta, angle made by OP is theta, projection is on this line, therefore phi. on this line, theta and phi remains constant, but value of r varies from point to point. Therefore, this is r curve. Then next curve, theta curve. The intersection of r constant is a spherical surface, and phi constant. Phi constant is a half plane with one edge along z axis. An intersection of this sphere and half plane. This sphere and half plane intersect along this half circle, this red half circle, intersect along this half circle. And this half circle is theta curve, because along this curve, when we move from point to point along this curve, value of theta varies. Value of theta varies. Let us see in detail in this figure. This spherical surface and this is half plane intersect along this half circle. If the point is here, then angle made by line OP, let this point is OP, then angle made by this line is theta. Put perpendicular is here, value of this is phi, with angle made with x-axis is phi. If the point P is moved here, then theta is increased, but r is same, and foot perpendicular is again on same line. Therefore, phi remains same. If the point is moved here, again foot perpendicular on same line. Therefore, phi is constant. Distance from origin is constant. That is r constant, phi constant. That is along this red half circle, value of theta and phi, all points on this red circle have same value of theta and same value of same value of r and same value of phi, but value of theta varies from point to point. Therefore, along this half circle, only theta coordinate change while r and phi remain same. Therefore, this is theta curve. Then the third curve, phi curve. This phi curve is the intersection of r constant, that is sphere. R constant is a sphere, and phi constant. Phi constant is a cone. Then intersection of sphere and cone. If we visualize three-dimensionally, then intersection of sphere and cone is a circle. In this figure, this red circle is phi curve. Along this phi curve, only phi coordinate change while r and theta remain same. If you observe here, then all points on this circle are at the same distance from origin. Therefore, r is constant. Angle made by line connecting this point with origin remains same, that is theta constant. Only projection from different point is in different region of xy plane. Therefore, phi varies from point to point. Phi varies from 0 to 360 degree. That is, when projection is on x-axis, value of phi is 0. When along this 0 to 90 degree, when projection is on negative y-axis, then 270, and in this region it is between 270 and 360. In this way, phi varies from 0 to 360. This third curve, phi curve. Next topic, transformation equation. In this topic, we have to derive the relation, that is mathematical relation between spherical polar coordinate system and Cartesian coordinate system. We have already seen these two coordinate system. In Cartesian coordinate system, coordinate axis use x, y, z. Then distance of point P along x-axis is x coordinate, along y-axis is y coordinate, and along z-axis is z coordinate. In this way, this distance QM is x, same as ON. This distance ON is x. Distance OM or NQ is y coordinate, and this distance PQ or this distance is z coordinate. This way, these three coordinates in Cartesian coordinate system x, y, z. Just we have seen spherical polar coordinate. R is the distance of point P from origin. theta is angle made by this line OP with Z axis, and phi is angle made by this projection OQ with X axis is phi coordinate. Let us derive Cartesian coordinates in terms of spherical polar coordinates. If you observe geometry of this figure, then this angle ZOP is theta. This angle ZOP is theta, and this is a parallelogram. Therefore, this angle OPQ is also theta. This angle OPQ is also theta, and this angle is 90 degree. This angle is 90 degree. That is, from figure, sine theta is equal to, this is hypotenuse. This R is hypotenuse. Then from figure, sine theta is equal to OQ, this front side. Sine theta is equal to this front side upon hypotenuse. That OQ upon R. Sine theta is equal to OQ upon R. Therefore, we get OQ is equal to R sine theta. This OQ is equal to R sine theta. Therefore, this is also R sine theta. Then this angle ONQ is 90 degree. ONQ, this right angle triangle. Therefore, this angle ONQ is 90 degree. This angle is 90 degree. Therefore, this OQ is hypotenuse. This OQ hypotenuse, and its value is R sine theta. Therefore, from figure, cos phi is equal to adjacent side. This is ON. Cos phi is equal to adjacent side upon hypotenuse. That is OQ upon ON upon OQ. Sorry, cos phi is equal to ON upon OQ. This cos phi is equal to ON upon OQ. But OQ is R sine theta, and ON is X. ON is X and OQ is R sine theta. If we substitute ON is equal to X and OQ is equal to R sine theta, then we get this first equation. First equation, X is equal to R sine theta cos phi. That is Cartesian coordinate X in terms of spherical polar coordinate R theta phi. Again, from the same triangle ONQ, from triangle ONQ, sine phi is equal to this front side NQ. This front side is NQ upon hypotenuse R sine theta. That is OQ. That sine phi is equal to NQ upon OQ. NQ is Y. This NQ is Y, and OQ is R sine theta. Therefore, sine phi is equal to Y upon R sine theta. Then we get Y is equal to R sine theta sine phi. This is the second equation. That second coordinate Y in terms of R theta phi. Again, from this triangle OQP, from this triangle OQP, cos theta is equal to from triangle OQP, this angle is 90 degree. For this R is hypotenuse. Cos theta is equal to adjacent side PQ. Adjacent side PQ upon hypotenuse R. That is OP. PQ upon OP. PQ is Z. PQ is nothing but Z, and OP is R. Therefore, cos theta is equal to Z upon R. Therefore, Z is equal to R cos theta. This is the third coordinate in terms of spherical polar coordinates. In this way, we get X, Y, Z in terms of R theta phi. The first equation, X is equal to R sine theta cos phi. The second equation, Y is equal to R sine theta sine phi. And third equation, Z is equal to R cos theta. Let us derive spherical polar coordinate in terms of Cartesian coordinates. That is, we have to derive R theta phi in terms of XYZ. Just we have derived these three equations. X is equal to R sine theta cos phi, Y is equal to R sine theta sine phi, and Z is equal to r cos theta. Using these three equations, we have to obtain spherical polar coordinates in terms of Cartesian coordinate. For this, we have to first simplify this equation. X square plus y square plus z square. Substitute x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. Then we get this r square sin square theta cos square phi plus r square sin square theta sin square phi plus r square cos square theta. From these first two terms, or from the first two terms, if we take r square sin square theta common, r square sin square theta common, then in bracket cos square phi plus sin square phi. But cos square phi plus sin square phi is equal to 1. Therefore, the equation simplified to r square sin square theta plus r square cos square theta. Again, from these two terms, take r square common. R square common. Then in bracket sin square theta plus cos square theta. But sin square theta plus cos square theta is 1. Therefore, x square plus y square plus z square is equal to r square. This way we get first equation, r is equal to square root of x square plus y square plus z square. This is the first coordinate r in terms of Cartesian coordinate x, y, z. Let us obtain equation for second coordinate. For this, consider the equation, third equation, z is equal to r cos theta. As z is equal to r cos theta, therefore we may write cos theta is equal to z upon r. Therefore theta is equal to cos inverse z upon r. Or theta is equal to cos inverse z upon r. But r we have already derived in terms of x, y, z. Substitute this value of r here. Then we get theta is equal to cos inverse z upon square root of x square plus y square plus z square. In this way, this is second spherical polar coordinate in terms of Cartesian coordinates x, y, z. Then to obtain third coordinate, take the ratio of these two coordinates y and x. Y is r sin theta sin phi, x is r sin theta cos phi. R sin theta get cancelled, and sin phi upon cos phi is tan phi. Therefore, y upon x is equal to tan phi. Y upon x is equal to tan phi. Therefore, phi is equal to tan inverse of y upon x. Phi is equal to tan inverse of y upon x. This way, this third spherical polar coordinate in terms of Cartesian coordinate y and x. In this way, we have derived 6 equations. The first 3 equations, Cartesian coordinate in terms of spherical polar coordinate. X is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. And 3 equation for spherical polar coordinates in terms of Cartesian coordinate. At r is equal to square root of x square plus y square plus z square. Theta is equal to cos inverse of z upon square root of x square plus y square plus z square, and phi is equal to tan inverse y upon x. That's all in this lecture. Thanks.